So, good morning, everybody, to the second day of this wonderful event to honor Sergiu. The first talk of the day will be Gustav Holzegel from Imperial College London, and he will talk about the linear stability of the Schwarzschild solution under gravitational perturbations.
Yeah, thank you very much. First, I want to thank the organizers for inviting me to speak. It's a great honor. Is this better? Yes. Okay, sorry. Right, so let me start the talk by telling you about another birthday kid, if you want, who just had his 100th birthday, namely the Schwarzschild space-time, which is the simplest non-trivial solution of the vacuum Einstein equations, Ricci of G is equal to 0. So just to recall, I mean, I wrote the line element here for you. The metric is spherically symmetric, so this is just the metric on the round sphere. It's also static. It doesn't depend on t. It's asymptotically flat. So for large R, you see that you approach the Minkowski space. And there also seems to be something going wrong at R equals 2m, but that's just a coordinate singularity. And if you look closely, then you understand that the hypersurface R equals 2m is in fact a null hypersurface of the spacetime, which separates two regions from one another, one from which you can communicate with outside observers and one from which you can't. And well, this is most easily illustrated by these Penrose diagrams, which are a conformal depiction of the spacetime. So light rays are at 45 degrees. Every point in this picture corresponds to a two-sphere, and this is precisely the black hole region that I was talking about. If you're in here and you draw the future light cone, you see that you will have to go to R equals 0. You can no longer communicate with observers at R equals infinity here on R infinity, and this is the black hole exterior. Okay, so this is the Schwarzschild space-time that the talk will be about. Well, two remarks, and both of them were sort of mentioned in Igor's talk already yesterday. Well, I say non-trivial solutions, or what's the trivial solution? Well, the trivial solution is Minkowski space, and we heard yesterday about the monumental work of Sergiu with Dimitri Christodoulou, who proved nonlinear stability of the Minkowski space. But that's really the only nonlinear stability result that we have for the Einstein equations without symmetry. So we of course want to know how the dynamics of the Einstein equation behaves near the next non-trivial one, namely the Schwarzschild solution. And there's a little caveat that we also heard about yesterday. The Schwarzschild family sits, in fact, as a one-parameter family in a larger family, in the two-parameter family of Kerr solutions, which are parameterized by M and A, mass and angular momentum per unit mass. But if we go to this family, then we have rigidity. Again, this is work of Sergiu that was mentioned yesterday. So if you are a member of this family, then at least in the neighborhood, there are no other stationary solutions, only those which are in the family. So this result already emphasizes the central role that the Kerr solution plays, and of course the big open problem is to show the dynamical stability of the Kerr family. Okay, I'm not going to say too much about the nonlinear problem, only at one point later in the talk. So I want to go straight to the result and to the linear theory. So here is the first version of the theorem that we're going to prove in the next hour. So we consider the system of equations obtained by linearizing the Einstein equations with respect to a fixed Schwarzschild metric of mass m. Okay, we consider initial data for this linearized system. We have to find well, suitable norms in which we measure the size of the data. And then the claim is that the evolution converges to a member of the linearized curve family of solutions up to an infinitesimal diffeomorphism. And moreover, this infinitesimal diffeomorphism will be uniformly bounded in terms of the initial data that we started from. Okay, so this is a very rough thing, and in particular, I will have to explain you all these words that I'm using here. So I will start by explaining to you the procedure how we linearize the Einstein equations. Then, well, I'll tell you how to do analysis for this big linearized system, and I'll tell you in particular about what I mean by these infinitesimal diffeomorphisms. And well, then give a more precise statement of the result. Okay, so that's the rough plan for the next 20 minutes or so. I'll explain the linearization procedure, which will lead us to the system of equations, and then I'll tell you about certain special solutions to this linearized system. And finally, I'm going to tell you how to do estimates. Okay. So what is the linearization procedure? Let's go back to the Schwarzschild metric, and the Schwarzschild metric can also be written in double null coordinates, so-called Eddington-Finkelstein coordinates. And let's fix these UV coordinates of the Schwarzschild family, and consider a one-parameter family of Lorentzian metrics, which we express in double null coordinates. So clearly U and V here are null coordinates. Constant U is null and constant V is null, and they intersect in spheres with metric G slash, which of course is no longer the round metric as it is for Schwarzschild. And we have this Labs function omega, the metric G, and a vector on these two spheres B, which sort of parameterize the dynamics of this one parameter family. And G at 0 is just a Schwarzschild metric of mass m. So this is a choice of coordinates, a choice of double null coordinates. Any metric can be locally put into this form. And why do we decide to sort of perform the linearization with respect to these double null coordinates? Well, it's because of their success. Okay, they've been employed with large success in the analysis of the Einstein vacuum equations, starting with Klainerman and Nicolau in the context of the stability of Minkowski space, then the work of Christodoulou on the formation of trapped surfaces, the follow-up work by Klainerman and Rodniansky, the theory of impulsive gravitational waves of Luke and Rodniansky, and also results on the interior of black holes. So they've been employed very successfully. So this is why we use them in this problem as well. Okay, so we have our one-parameter family. Now I want to associate with this one-parameter family a null frame or family of null frames, which is given by the following, by E3. E4 and EA. So these are the two null directions. So they're tangent to the generators of the hypersurfaces of constant U and constant V. And this is just a frame tangent to the spheres. And what I'll do is I'll express all the connection coefficients of this metric with respect to that frame. So to give you an example. So if you look at a null cone, of constant U, then you know that this null cone is foliated by these spheres S2UV. Okay, and this quantity chi that I've written there is nothing but the second fundamental form of how these spheres sit in the cone CU. So I construct all these connection coefficients in a geometric fashion, and so this is a symmetric tensor on the sphere. I can decompose it into its trace and to its trace-free part, And let me also introduce the following notation. So whenever I write bold, then this is the full metric. When I write unbolded quantities, these are the Schwarzschild values. And when I write little ones, can you see them, that there are little ones over the quantities? I hope so. So these are the linearized quantities. That is to say, these are the quantities to order epsilon. Okay, so a full list of these linearized metric and connection coefficients that will appear are these ones here. So you remember from the previous, so you have this omega, you have the metric G, and you have this vector B. So these are just the linearized versions of these quantities, and these quantities here, at least the first two of the first four I explained to you. So these are the linearized metric and connection coefficients. And finally, we're going to do the same thing for the or similar thing for the curvature components. That is to say, so Ricci vanishes, so we only have the Weyl curvature, and we're going to decompose the Weyl curvature tensor with respect to the null frame that I gave to you. So that this gives you these components alpha, alpha bar, beta, beta bar, rho, and sigma, which are again familiar from stability of Minkowski space. And if you look at what these quantities are, if your metric is Schwarzschild, then so epsilon is equal to 0, then you see that well, the only non-vanishing quantity is this curvature component rho, and it has this value minus 2m over r cubed. Okay, and again, I will denote the linearized quantities, so these quantities to order epsilon with the 1 on top. Okay, so that's so far that's only been definition. So what is the system of equations that we're estimating, that we're actually doing estimates on? Well, this again connects with Igor's talk from yesterday. So the way we're going to estimate is we're going to estimate actually the curvature components which satisfy the Bianchi equations, and the connection coefficients we're going to estimate via the structure equations. Just to give you an idea of what is involved, so if you take this system of equations for the curvature and for the connection coefficients, and you formally linearize this system, then you arrive at the system 1. So your background has, say, connection gamma and curvature W. So from linearizing the first equation, well, you get the background connection and the linearized curvature, but you also get a term from the background curvature and the linearization of the connection, which is this term, right? And similarly, you can linearize the second equation. So now you observe a key difference between, let's say, the linearized version of stability of Minkowski space and the problem that we want to do, linear stability of Schwarzschild. And that is, if you linearize with respect to Minkowski space, then the background curvature is 0. So this term here drops out of the linearization, and the first equation actually decouples, right? It only involves linearized curvature, but not the linearized connection coefficients. And that's sort of simplifies the problem tremendously. So then there is this Bell-Robinson tensor that was also talked about yesterday. There are certain conservation laws for the linearized curvature, and in fact, this was a precursor to the stability of Minkowski space, a paper by Christodoulou and Klainerman, which studied precisely these linearized spin 2 equations. Okay, but for us, the equations couple. So around Schwarzschild, of course, the background curvature is non-zero, so we have coupling of these two equations even at the linear level. And this destroys all these nice variational structure and the conservation laws. Okay, I'll stroll through these very quickly. I just want to give you an impression of what the equations are that you're finally deriving. So here are some of the null structure equations. So here is this linearized component chi hat that I introduced earlier, and you see this is a transport-like equation. You have a curvature component, linearized curvature on the right-hand side, this component alpha, and you have an equation in the 4 direction. So remember that the 3 and the 4 direction. So for me, This is the horizon, so this is the E3 direction, and this is the E4 direction. So you have transport equations for the Ricci coefficients, which involve curvature on the right hand side. You have a lot of them, and finally for the Bianchi equations, remember these were the equations for the curvature components, so these will involve alpha, beta, and so on. And I just want to stress one thing. So this term here is precisely the coupling term, which couples sort of without this term, this would be an equation just for curvature, just for the curvature. Oh.
When you say this term, we can't see the left.
Oh, really? Well, I press as hard as I can. Well, does anybody have another pointer, maybe? It would be. Okay, I'll try to be more precise with which terms I mean in the meantime. So I just mean the last term in the first equation, right? If you look at the first equation, you see that all the terms involve just sort of Schwarzschild. So okay, I haven't told you that what omega is. So omega squared is 1 minus 2m over r, so it's a weight that vanishes on the event horizon, which you remember is located at r equals 2m, and r is just the Schwarzschild r. So if you look at the first equation, you see it's an equation for the curvature components, except for the last term, which involves the component chi hat, which is a linearized connection coefficient. Okay, and this was the coupling that I was alluding to earlier. Okay.
Maybe this will work.
Okay. Maybe I can just use the laser thing for this.
Oh, you know what it is? It doesn't look. You can't see it on the screen. It's very dim on the screen.
Now this one recovered.
Okay.
Okay.
Maybe it won't. This won't work because I took out.
Oh, so now.
Okay, well, good luck.
Okay, let's see. Okay, I just presented you the equations, and you saw lots of these derivative operators in the 3 and in the 4 direction. Of course, you don't have to remember what they are. This slide is merely for completeness, so that everything is defined. So in particular, there are these two angular operators, d/1 star and d/2 star, which map. So the first one maps a pair of functions, rho and sigma, to a 1 form, and the second maps a 1 form psi to a symmetric traceless tensor. So they'll appear briefly later, I think, but otherwise you don't have to remember them. Okay, so we have this huge system for linearized metric components, linearized connection components, and curvature components. Now, this system is, in principle, well known in the physics literature. It's just that, physicists, they don't like PDEs. So what you find in the physics literature is mode decomposed versions of these equations. So whenever you see a time derivative, a physicist will write I omega, and they also decompose into spherical harmonics. So you also find it in a different notation, which is sort of competing with the Sergiu Klainerman notation, the so-called Newman-Penrose formalism. But let's stick to the notation that I introduced. Okay, so the point I want to make here is that you don't have to go to, of course, to decompose into modes. The system is well posed in physical space, and in fact, that's the first thing that we sort of observe. So we in fact look at a characteristic problem. So this is V equals V naught and U equals U naught. So you can prescribe characteristic initial data for the linearized system on an initial cone, and then we're interested in the solution that gets launched from that initial data set and the properties. Okay, so how do you do analysis for this system of gravitational perturbations? Well, so the first thing I have to tell you is something about special solutions. And let me start by talking a little bit about so-called pure gauge solution. Pure gauge solution. So I already told you that we're making this choice of a double null foliation. Now, let's use this. If you look at again the metric in the UV theta 1 theta 2 coordinates, then it turns out there's still residual coordinate transformation, so changes of UV theta 1 theta 2 coordinates, which preserve this double null form of the metric. Okay, so if you want to think about them in terms of linear theory, you can think about, okay, I'm going to make an infinitesimal coordinate transformation. I'm sending u to u plus epsilon times some function of the other coordinates, and v to v plus epsilon times some function of the other coordinates. And if I'm careful, then I can preserve this form of the metric. Of course, omega is going to change to order epsilon, g slash is going to change to order epsilon, and b is going to change to order epsilon. Right? But I can read off what this is, and this is a solution of the system of gravitational perturbations. And this is what I want to call a pure gauge solution, because it's a diffeomorphism in the nonlinear theory, which we see in linear theory as a particular kind of solution. And the nice thing is you can actually work out explicitly what these pure gauge solutions are. So I've given you this little lemma here, which just tells you that if you have a function f which does not depend on u, then if you set g slash hat to be this, square root of g this, and so on and so forth, I mean, you can compute what all the connection coefficients and curvature components are. This is a solution of the system of gravitational perturbations, and I want to call it a pure gauge solution for the reasons that I mentioned. So this is what the diffeomorphism invariance of the nonlinear theory. The other special solution that I want to emphasize are the linearized Kerr solutions. Okay, so you can take the Kerr family of solutions, express them in the double null coordinates that I mentioned, and then linearize with respect to the angular momentum parameter. Okay, you read off what the solution is to linear order, and you have your what you call the linearized Kerr solution. And again, you can compute this explicitly. I've given you the formulae here. The point is that essentially the solution can be parameterized by the L equals 1 spherical harmonics. And the other important remark here is that you can detect the existence of non-trivial Kerr solutions directly at the initial data. Okay, in fact, you can go to the, for instance, in this picture, you can go to the horizon sphere, you can look at the curvature component sigma, and you can look at the L equals 1 modes of sigma, and that will tell you, whether you have a Kerr solution in the initial data or not. Okay, this is special solutions. I mean, this is an important sort of caveat already, because it tells me, naively I might think, okay, I want to prove decay, I put initial data, and my solution will hopefully converge to 0, it will decay. But in view of the existence of these pure gauge solutions and the linearized Kerr solutions, the best thing I can expect is that I converge to one of these pure gauge solutions and a linearized Kerr. Okay, so that's important to keep in mind. Okay, so where are the estimates, if you like? So the next thing that we'll look at is what's called gauge invariant quantities. So if you look at these curvature components alpha and alpha bar that I introduced, well, they satisfy the first order Bianchi equations, but if you take another derivative, you'll observe that they satisfy wave equations. And remarkably, alpha and alpha bar satisfy decoupled wave equations. Okay, and the wave equation that alpha satisfied, I've given you schematically here. So it's essentially the usual box applied to the component alpha, but there's a first order term, which is here, and there's also a potential term. Okay, but it's already remarkable that these quantities decouple from the system, and that they're also gauge invariant. So by this I mean that the pure gauge transformation that I introduced earlier to you, they're not seen by these quantities alpha and alpha bar. They're always zero. Okay, so that's very good. So I have a decoupled equation, but unfortunately, well, not all wave equations are equally good, and this one is not a good one. So it was not known even for how you prove uniform boundedness for solutions of this linear wave equation on Schwarzschild. Okay, so and the reason is sort of hidden in this first order term, if you like. Okay, so how do we actually estimate solutions to the Tarkovsky equation? So that's the first step in our work. In fact, you should keep in mind that this problem of proving decay for solutions of the Tarkovsky equation is a problem that you can consider completely independently of the system of gravitational perturbations, right? Because it's a decoupled equation, and you can say, okay, I'm just going to study this equation and forget about that, it arose from the system of gravitational perturbation in the sense that alpha satisfies this decoupled equation. And that's exactly how our paper is written, that we first sort of consider general solutions of the Tarkovsky equations and prove decay for them, if you look at the paper. Okay, so how does one prove estimates for the Tarkovsky equation? Well, there is a remarkable hierarchy of these gauge invariant quantities which allow you to prove decay estimates for alpha and alpha bar, and this is what I'm going to explain next. Okay, so you start from the quantities alpha and alpha bar, and you construct from alpha and alpha bar this pair of quantities psi and psi bar by simply applying a derivative operator in the 3 direction with some weights to the quantity alpha. For now, you can forget about the right-hand side. The right-hand side is if you're also willing to use the system of gravitational perturbations. But what I'm going to say in the next 10 minutes or so, you can just restrict it to the Tarkovsky equation without sort of the system of gravitational perturbations. So you have these quantities psi and psi bar, and then it's annoying. Then from psi and psi bar, you construct the quantities p and p bar by again applying another 3 derivative to the quantity psi, or a 4 derivative to the quantity psi bar. Okay, so what you've done in total is p is some second order operator applied to the Tarkovsky quantity alpha, and similarly p bar is a second order operator applied to alpha bar. Again, the formulae 3 and 4, you can compute them if you're willing to bring in the entire system of gravitational perturbations. So again, these transformations in the form that I presented to you, they're new, but at the level of mode solutions, you can sort of distill them out of the work of Chandrasekhar. What's remarkable, so why did we do this second order transformation? Well, what's remarkable is that the quantities p and p bar constructed out of alpha and alpha bar, they satisfy, again, a decoupled wave equation, which is called the Reggie Wheeler equation, and this equation is a good wave equation. Okay, this is a wave equation for which all the theory that has been developed in the past 10 years for wave equation on black holes actually applies. Okay, in particular, what does it mean? Well, this equation does admit a positive conserved energy and an integrated decay estimate. Okay, moreover, p and p bar, I told you that alpha and alpha bar are gauge invariant. P and p bar are also gauge invariant, so they don't see these pure gauge solutions. Okay, that's very good. So proving decay for these for p and p bar is in particular consistent with the existence of pure gauge solutions. And moreover, they're symmetric traceless tensors, so they don't see the L equals 1 spherical harmonics. So its decay for these quantities is in particular also consistent with the with these Kerr modes. Okay, and the last important point is that once you've proven decay for P and P and P bar, you can use this hierarchical structure here, these transport structures. So once you have P, you can use the defining equations for P as as equations which will give you estimates for psi and psi bar respectively, and then you go one level up in the hierarchy and you prove estimates for alpha and alpha bar. Okay, so the hierarchy allows you to finally obtain decay estimates for all gauge invariant quantities, alpha and alpha bar, psi bar, and P bar. Okay, a few words about the analysis of the Reggie Wheeler equation. I've given you the Reggie Wheeler equation there. In particular, you see that in 5, you see that there is no first order term there. In fact, it's not hard to see directly just by multiplying this equation by dt phi that there exists a positive conserved energy. And I'm going into the details on the next couple of slides. But all the geometric insights for the wave equations, they you can use them for the Reggie Wheeler equation. So you have a redshift estimate near the event horizon, which allows you to improve the estimates near the event horizon, and there also exists an integrated. Yeah. So we're doing the estimates directly at the level of tensorial quantities. It's just that in the literature. Sorry.
Is this a bit misleading?
Well, I just wrote this because the way the Reggie Wheeler equation appears in the literature is typically for a scalar equation. So I just want to make that connection. But what we do in the paper, if you look at it, is we're doing estimates directly for symmetric traceless tensors. Yeah. Okay. So actually, an integrated decay estimate was already shown for the Reggie Wheeler equation in work of Blue Soffer and myself, and this is precisely where the geometric phenomenon of trapping enters. So once you have these two estimates, the energy estimate and the integrated decay estimate, you're essentially home. You can use the black box results of Dafermos, Rodniansky, Volker Schlu, and Mosfidis to get any polynomial decay statement that you would like, pointwise statements, and so on and so forth. Okay, so let me tell you a little bit, maybe 10 minutes or so, about the linear wave equation on black holes. Just to give you an idea of what are the techniques and how the black hole geometry enters into the estimates that you have to do. What you have to keep in mind is that everything I say about the linear wave equation now, it applies to the Reggie Wheeler equation. I mean, that's the crucial point. But if you haven't seen how to do estimates for the wave equation or what the difficulties are, in the next 5-10 minutes you'll hear something about that. Okay. So what people have looked at in the past 10 years in this field is mostly the linear wave equation, scalar linear wave equation. Okay, I'm sorry, that doesn't seem to work. Scalar linear wave equation on a fixed member of the Kerr family, a subextremal member of the Kerr family, and what's been obtained in over a period of 8 years or so is the following. If you look at just the scalar wave equation on a Kerr space-time, then solutions to this equation decay on the black hole exterior, and they decay at polynomial rates. And these polynomial rates are sufficiently strong to be able to sort of deal with nonlinear problems which have a structure that you expect to see in the nonlinear problem. But it's a scalar equation, right? I mean that's that's what I want to put emphasis on. Okay, and the result was proven in several stages, first for Schwarzschild, then for the very slowly rotating case, and finally in last year or two by Dafermos, Rodniansky, and Schlapp and Grothman in the full sub-extremal case. So there has been a lot of other work in this direction as well. So the theorem fails in the extremal case. Work by Aretakis. You can try to sort of go away from the scalar problem and prove something for the Maxwell's equation, which has been done at least in the slowly rotating case. And you can also look at other backgrounds, so spacetimes with cosmological constant. Well, there's some surprises there in terms of the decay, but that's not the topic of this talk. So let me just give you a flavor of why that problem is sort of difficult. The problem of establishing decay, even for the scalar for the scalar wave equation, and let me restrict also to the Schwarzschild family. Okay, so this excludes some of the difficulties of the Kerr geometry, but you get a good picture of what are the main difficulties. So for this, it's fruitful to go back to Minkowski space for a second. So in Minkowski space, if you wanted to prove decay, one way is to use sort of two key estimates. The first is simply energy conservation, the first equation that I've written there. And the second is what's called the Moravec estimate, about which we heard also a lot yesterday, or integrated local energy decay estimate. So on the left-hand side, you just see the local energy in a ball of radius r integrated in time, and on the right-hand side, you just see the energy at t equals 0. So if you wanted to, so now let's go away from Minkowski space and look at the Schwarzschild case, so wave equation on Schwarzschild. So suppose you wanted to try and reprove these two estimates. Well, already sort of getting these two estimates requires understanding two geometric phenomena. One is the redshift effect near the event horizon, and the other is the trapping of null geodesics. Okay, so what are these two phenomena? Well, the first one, the redshift effect, is to do with the event horizon. So if I look at two space-like slices, say sigma naught and sigma t, well, I can apply so my vector field d by dt for Schwarzschild, I said in the beginning that Schwarzschild is static, so it has a killing field which is causal on the black hole exterior. So I will have a conservation law which relates an energy on sigma 0 to an energy on sigma 1, and a boundary term on the horizon. But the vector field d by dt is such that it becomes null on the event horizon. And what this means is that if you apply the d by dt energy identity, you get an energy identity, but you have a weight in the energy identity which degenerates on the event horizon at r equals to m. So your energy loses control near the event horizon. In particular, having just this estimate is consistent with psi growing along the event horizon. And the redshift effect is precisely about finding a geometric vector field which allows you to remove this degeneration. So I'm not going to say more about that. The other geometric phenomenon that you have to understand for the scalar wave equation in the Schwarzschild case is the trapping phenomenon. So if you look at null geodesics on your Schwarzschild background, then you'll find that there are some which for all times remain in the time-like hypersurface at r equals 3m. So they are trapped at a finite r, and they neither escape through the event horizon nor through infinity. And if you think about the high-frequency approximation to the wave equation, you can imagine that the energy concentrates along these null geodesics for arbitrarily long times, which is clearly an obstruction to decay. And what this means is that in proving this integrated local energy decay estimate that I alluded to earlier, it means that you can prove such an estimate, but you lose a derivative, so you have to include sort of higher derivatives on the right-hand side of your estimate. So without this term, without the last term in the last formula, the estimate would be incorrect, and that's a result of Spearsky based on classical results of Ralston. So, okay, to cut the story short, you can prove such estimates, but they require a lot more work than in the Minkowski case, and you really have to understand the black hole geometry in order to prove the results. Okay, so that much about the wave equation. So where do we stand at the moment? Well, I showed you the system. I told you about these pure gauge solutions. I told you about the linearized Kerr solutions, and I told you about the gauge invariant quantities alpha and alpha bar. I then told you that from alpha and alpha bar, you have this hierarchy. You can construct the quantities p and p bar. They satisfy a nice wave equation, the Reggie Wheeler equation, to which the whole theory of the scalar wave equation applies, which I presented to you. So that's where we stand now. We have decay for the quantities p and p bar, which satisfy the Reggie Wheeler. And now I want to show you how to get decay for psi and alpha and psi bar and alpha bar. So that's the first theorem, if you like, about the gauge invariant quantities. So you look at the system of a solution of the system of gravitational perturbations, which arises from this characteristic initial value problem, and then the gauge invariant quantities p psi alpha and p bar psi bar alpha satisfy boundedness and integrated decay estimates. Okay, and you can also get polynomial decay. And we do in the paper. Okay, so how do you do that? Well, for p and p bar, I just told you that they satisfy Reggie Wheeler, so you have all the statements that you like. So let's look at psi. Well, psi, remember, satisfied this transport equation in the three directions. So nabla 3 psi was essentially equal to p. So you just multiply this equation by psi, and you get the equation that I've written over here. Okay, so the weights near the horizon and near null infinity, they are very important. So you have to you have to get them right. And now you're just squeezing in an r to the n into the bracket. You know that Ru, the derivative of the area radius with respect to u, is minus omega squared, and you get this equation. Okay. And in the last step, you just apply Cauchy-Schwarz on the right-hand side, which gives you this, and the psi term that you get from Cauchy-Schwarz you absorb by this term on the left. So this term has a 1/2 here. And now you see you're just going to integrate this. You're just going to integrate this equation in a region like this, say. Okay, so the integration in U will give you an initial data term and a future term, so you control the future term and the second term. The second term on the left is also positive, so you also control this term and the future boundary term here from the right-hand side. And what's the right-hand side? Well, the right-hand side is this the space-time integral over p. But I already told you that you have an integrated decay estimate for p, so you're using that you have control there on the right-hand side. Okay, and then you go one step up in the hierarchy. You do the same argument for alpha in the role of psi and psi in the role of p, and you get decay for alpha. Okay, so that gives you in particular the following corollary, that solutions to the Tarkovsky equations decay inverse polynomially in time, which was something that was not known before. Okay, very good. One final remark about the role of these Tarkovsky quantities alpha and alpha bar. Well, they actually capture the dynamics of the system in the following sense, that if you consider a solution which satisfies alpha and alpha bar is equal to 0 globally, and your solution is asymptotically flat, then you actually have to be linearized Kerr plus a pure gauge solution. Okay, so in this way, alpha and alpha bar really capture the dynamics of the system. Okay, so how do you estimate the rest? So we made progress. We've estimated gauge invariant quantities of this big system of gravitational perturbations. So how do we estimate the gauge dependent part of the solution? Okay, so here are the key ingredients that you need for that. Well, you first need a notion of asymptotically flat seed initial data. So in particular, you have to so when you specify initial data on this outgoing cone, you have to understand their decay towards null infinity, and you also have to understand sort of what decay rates you can propagate near null infinity. So that's what you have to understand first, and then well, suppose you specified some initial data. Now you want to prepare your initial data in a certain gauge. Okay, so what is the freedom that you have? Well, remember that you always have the freedom to add pure gauge solutions. And I have the pure gauge solutions explicitly. So what I'm going to do is I'm going to add to my solution to my solution S a pure gauge solution G with a roof down to obtain a solution S with a roof down, which is what we call initial data normalized. So in particular, by adding these pure gauge solutions, I can achieve that for my solution S hat, certain geometric quantities are 0 on the horizon sphere, for instance. Okay, and I can also ensure that, for instance, the sphere at infinity is a round sphere. Okay, so that the linearized Gaussian curvature is 0 on the sphere at infinity. So I can use these pure gauge solutions to have my solution S with the roof down to have certain properties. Okay, so I prepare the solution in this initial data gauge, and now I'm starting to estimate the quantities of the solution S with the roof down. So let's first estimate the quantity chi hat. Well, if you remember, there was a transport equation for chi hat that I showed you earlier, which said, well, chi hat satisfies an equation in the 4 direction with curvature component alpha on the right hand side, which is precisely what I've written here. Okay. Now, there's something bad. So you would think that, okay, I have control on the right-hand side. I proved decay for alpha, so I should be fine in now estimating in estimating chi hat. But this equation, so remember, this is an equation in the 4 direction. So I estimated, well, from data here in this direction, right? And what you see is that there is a factor in this transport equation which has a negative sign, which corresponds to what's called the blue shift, or an exponential growth factor for this equation. So this equation won't give me good estimates for chi hat, even though I know everything I like about alpha. Okay, and to get around this problem, you use something that also has a version for the wave equation. Namely, you commute this equation 7 by the redshift vector field 1 over omega d by du. And what you see when you do that is that if you commute, you will remove precisely this term. Okay, you'll get an equation for nabla 3 of the quantity chi hat, and this term will be completely gone. Okay, so now this went very well. We just eliminated this term, but you can actually do better. You can do it twice, and if you do it twice, you see that you see an equation for 2 3 derivatives of chi hat, but now this factor actually has a plus, which is an exponential decay factor. So that's very good, which is a version of the redshift effect. So this is familiar from the wave equation, where you do something similar, where you also commute with this vector field, and the strength of the redshift actually amplifies each time you commute. So you're using this principle here at the level of the transport equation. Okay, very good. So now remember that you're now estimating 3 derivatives of chi hat. So how do you estimate chi hat? Well, you estimate it from knowing what it is on the horizon and then going in the 3 direction from the horizon again via transport. And the fact that you know what chi hat is and nabla 3 of chi hat is on the horizon is related to the gauge invariant estimates that you already have, and the fact that you prepared the solution in the initial data gauge, which allows you, so there are certain conservation laws in linear theory along the event horizon, which allows you to control certain things a priori on the event horizon, and that's what you're using here. Okay, so that's very good. So for chi hat, we now have also boundedness and polynomial decay. So now we want to go to chi bar hat and see whether we can do the same thing there. But it turns out that for the quantity chi bar hat, you can actually only show boundedness. So this commutation argument doesn't work so well. In a way, it's tied to the redshift effect near the event horizon, so it's not too surprising that it doesn't work. So before I tell you the resolution of for this other quantity chi bar hat, let me give you an informal version of the boundedness statement. So for this gauge prepared, what we call the solution in the initial data gauge S sub hat, you can prove that all geometric quantities are bounded. Excuse me, are bounded. So I've just given 3 examples here: a metric coefficient, connection coefficient, and a curvature coefficient. And note the weights in R here. So what you're proving is really also a statement of asymptotic flatness. So you include you include the weights that you expect the solution to have near null infinity. Okay, so you have a boundedness statement for all quantities for the solution as hat. Now, if you want a decay statement for all quantities, the way to get this is to add yet again another pure gauge solution. Okay. So this time, remember, for the initial data gauge, the initial data gauge was determined completely at the initial data. So I constructed them in such a way that certain things held on the horizon sphere and so on. The future gauge is determined dynamically from the solution in the initial data gauge on the horizon. Okay, so I look at the trace of a certain geometric quantity on the event horizon for the solution S hat. And then I solve an ODE for some function, and this function, the solution to this ODE, will generate the pure gauge solution G hat. And if I add the pure gauge solution G hat to my solution, then all geometric quantities of S with a hat upstairs will actually decay. Okay, so the crucial point is that you have to add another pure gauge solution, and this pure gauge solution is determined dynamically from the evolution, and you can't sort of guess what it is just on the basis of initial data. And this was the reason why there was an obstruction that you can only show boundedness for some of the quantities, because you're actually not convert. So S with the roof downstairs doesn't converge to 0, but converges to a pure gauge solution. Okay, so here's the summary statement of the theorem. So you consider a solution of the system of linearized gravity around Schwarzschild, general asymptotically flat initial data. The first part was the statement about the gauge invariant quantities. You have decay for Reggie Wheeler and the Tarkovsky equations. If you prepare your solution in the initial data gauge, that's the second part of the statement, then you have a boundedness statement, including weights near null infinity. And finally, part 3, if you add a dynamically determined pure gauge solution, then all quantities of the system of this future normalized or horizon normalized solution actually decay. And now you really decay to a member of the 4-dimensional family of standard linearized Kerr solutions. And again, as I said earlier, you can read off what they are at the level of the initial data. So you can if you prefer, you can subtract them right from the beginning. Okay, and another crucial point that one should emphasize is that, okay, you've added a pure gauge, you've added a dynamically determined pure gauge solution. The important thing is that we control this pure gauge solution that you're adding, so you're proving also uniform boundedness of this pure gauge solution that you're adding. Because a priori it could be the case that you have to add sort of larger, you have to do larger and larger coordinate transformation to ensure that you're converging to Schwarzschild. But this is not the case. We control the pure gauge solution that we're adding by initial data. Okay, so let me give a brief outlook on the nonlinear problem. Well, if you go now to the nonlinear problem, and while you consider, let's say, initial data for Schwarzschild, you perturb your initial data for Schwarzschild a little bit. Of course, because Schwarzschild sits in this 2-parameter family, you generally expect that you converge to a member of the Kerr family with a small but non-vanishing angular momentum. So the results don't apply directly to the full nonlinear problem, but you can make a conjecture as far as the you can make a restricted nonlinear stability conjecture, and that's what I've written on this slide. So since we understand the linear problem so well, you would expect that you can construct a finite codimension subfamily for which you converge actually to Schwarzschild. Okay, and the precise statement is here. So the maximum development of such perturbations will have complete null infinity and regular event horizon, and you converge on the black hole exterior to a nearby Schwarzschild metric. Okay, so in particular, this should construct the set of all nearby data which converge to Schwarzschild. So you cannot do all, but you can do a finite codimension subfamily according to this conjecture. Okay, so I have I have a little epilogue, but maybe I'll in view of the time, I just have 2 minutes. I'll skip the epilogue. I mean, you can ask me about it, but okay, thank you.
So are there any questions? Sergiu, maybe say something about the epilogue.
The epilogue. Okay, so the epilogue just suggests a little bit of an orthogonal approach to this problem. I mean, it's something that we don't use for the result that I presented, but it is something that I think will have applications in these kinds of problems. And this has to do with the fact that there are actually conservation laws for the system of gravitational perturbations, which are at the level of purely the linearized metric and connection coefficients. So if you remember, the proof used sort of a lot of these decoupled equations and so on. That's what I was presenting to you. But if you stare long enough at this system of gravitational perturbations, you see that there are also certain conservation laws which are hiding in this system. So I've written 2 fluxes there. So these are fluxes that you see on. So this is V0. V1, U0, U1. So what I've written there are certain fluxes, fluxes on null hypersurfaces. Okay, so these fluxes they don't look very nice. In particular, they don't look coercive, right? You have some quantities which look manifestly positive, but then you have some which look manifestly negative, and some which don't have a sign. What you have is that these fluxes are related by a conservation law. So the flux, the initial data flux here is equal to the flux on the future null hypersurfaces. Okay, so the point is, okay, that's a nice conservation law, which is a remnant of the fact that the full theory arises from a variational principle, and your background has a killing field d by dt. And the point that I want to make is you can exploit these conservation laws together with the pure gauge solutions in order to get control on certain fluxes on the event horizon and on null infinity. So you have to take certain limits. So first you have to understand how these fluxes change under pure gauge transformation. Okay, so it turns out that the fluxes that I've written down, they're actually invariant, or they're invariant up to boundary terms here and here if you go to a different gauge. I'm pretty sure it does. I'm pretty sure. But the problem with the canonical energy that they have is always that they can't show that it's positive definite. Okay? What I'm claiming is that you can see a positive definite quantity once you take the limit. I mean, you have to push this null hypersurface to null infinity, and you have to normalize your gauge on this cone. Okay, if you do these two things, I mean, in a nutshell, you change the gauge on this ingoing null hypersurface. It changes up to a boundary term, so you're seeing a boundary term here, and this flux on null infinity, you can show that this flux in the limit is the flux in the limit as you go to null infinity is the flux of chi bar hat squared plus a boundary term. Okay, and in the limit, this boundary term that you get from changing the gauge here and the boundary term that you get here in the limit, this boundary term cancels, and that's what gives you a positive definite quantity. Okay, so in I mean, okay, I don't know whether the conservation law that I've written down, whether this actually is the canonical energy. I mean, there can't be so many conservation laws, so you would think the two are certainly related. But okay, I'm.
Any other questions? Well, if not, then we'll break until 11 o'clock for chili oil. Coffee break till 11.